right, good morning, everyone. Let's get started. So we're continuing our discussion on the two-user degraded broadcast channel. First, we derived the superposition coding inner bound for general two-user broadcast channels. And now we were looking at outer bounds for the two-user degraded broadcast channel. So we are going to show that that basically the superposition coding technique achieves the entire capacity region of the two-user degraded broadcast channel. So we already derived one half of the outer bound. So in the previous class, we showed that we showed two things. First, that if these two conditions are satisfied, so if R1 is less than or equal to IXY1 given U, and R2 is less than or equal to IUY2 for some P XU, then the sum rate is also upper bounded by the mutual information between X and Y1. Right? So this rate region essentially corresponds to the superposition coding rate region. And we also showed that using two techniques, one Fanos inequality and the other by identifying U in a particular manner, by choosing a particular U, we showed that NR1 is always has to be less than or equal to the mutual information between X and Y1 given U bar, sorry, N times I of X, Y1 given U bar for a particular U bar, which can be fairly large. So it depends on N. So U bar is equal to W, which is a uniform random variable on 1, 2, 3 up to N. M2, L2 is basically the message corresponding to user 2, and Y1 through I minus 1. Right? So in particular, so U bar satisfies the following Markov chain. So U bar X I, so U bar I X I Y1 of I, Y2 of I, these form a Markov chain in the following order. Right? And this is true for all I going from 1, 2, 3 up to N. Right? So we had this upper bound on N times R1, and now we're going to derive a similar upper bound on R2. And this will effectively give an upper bound on, or will give an outer bound on the capacity region. So no matter how you choose your encoder and decoder, if you want the probability of error to be vanishing in N, then R1 must satisfy this inequality, and R2 must satisfy a similar inequality for sufficiently large N. Okay. Are there any questions from the previous class? So in this class, we'll see the second part of the derivation of the outer bound for degraded broadcast channels. And then I'll show how this reduces to, we'll see a simplification for the two user binary symmetric broadcast channel. So that's a special case of that's a special degraded broadcast channel. We discussed that in the very beginning of our discussion, and we've seen what the capacity, what superposition codes can achieve, and we'll see that that is indeed the capacity region of the binary symmetric broadcast channel. And after that, we'll see how this can be extended. So extended in the sense that the superposition codes are give you an achievable rate region, maybe not the best, but it certainly tells you one set of rate pairs which are achievable. And we'll see that that corresponds to the capacity region, of course, for degraded broadcast channels, but also slightly more general classes of broadcast channels which may not be degraded. So we'll see two classes of broadcast channels which generalize degraded broadcast channels, and in fact it will turn out that superposition codes are optimal for that class of channels. Okay, but for more general non-degraded broadcast channels, superposition codes may not achieve the capacity region. Uh, so and even and not just that, even when you go to more than two users, superposition codes do not achieve the capacity region of general broadcast channels. So it's only for degraded broadcast channels that superposition codes are optimal in the sense of achieving the entire capacity region. Okay, and later on, maybe in the next class or so, we'll look at Gaussian broadcast channels. Gaussian broadcast channels are always degraded. We'll see that, and therefore we can completely characterize the capacity region of Gaussian of two user Gaussian broadcast channels. All right. So let's continue with the proof of the outer bound. So we've seen in the previous class that uh, NR1 is less than or equal. We derived an upper bound on R1. And just to do a quick recap, we did the following. We started off with NR1, which is the entropy of the first message. And just by using Fanos inequality, we showed that this is less than or equal to the mutual information between the first message and y1n plus some quantity which is vanishing as long as the probability of error is vanishing in n. So bringing this probability of error is important because if the probability of error is not vanishing in n, then this could be much larger and you get a loose bound, right? But as long as the probability of error has to be small, uh, NR1 must be less than or equal to this mutual information between the message and Y1N, right? So in some sense, what this is saying is that uh, the, the amount of information that Y1N has to carry about the message is equal to the rate, is roughly equal to the rate at which you are operating, right? And that is something that you would expect. Right? As long as if you can reliably decode M1 from Y1N, then it must be the case that the entropy of M1 should be close to the mutual information between M1 and the received vector Y1N. Correct? And the trick that we used to proceed was by identifying the right auxiliary random variable U. So we started off with a u tilde such that ui tilde x of I, y1 of I forms a Markov chain, and really identifying the correct auxiliary random variable is as I mentioned, it's an art. It's just a trick. You try different auxiliary random variables till you get the right expression that you're looking for. And then we simplified this mutual information. We got a much better bound on this mutual information just by using some simple inequalities. We used the chain rule to expand this in terms of y1, and then we used the Markov chain property to bring in x of I and then eliminate some of the other variables. So we reduced that mutual information to the following mutual information. So summation I going from 1 through n of the mutual information between x of I and y1 of I given ui tilde. And again, by modifying the auxiliary random variable, we wrote this as n times some mutual information ix y1 given u bar, where this u bar is really large, has a really large alphabet. Okay, and we'll do something similar for uh, the second term as well, that is to get an upper bound on R2. All right, so we start with the following mutual information term I of M2 Y2N. So let's first start by expanding this just using the chain rule. So I of M2 Y2N is summation I going from 1 through N of I M2 Y2 of I given Y2 I minus 1. Okay. So now that we have this, let's think about what we want, right? So we know, so what our goal is to finally show that this quantity is upper bounded by the mutual information between u, or in this case u bar, and y2, right? So we want to show that this quantity is upper bounded by this quantity for some suitable u bar. We've already identified the u bar, so u bar is exactly this, right? As long as we can show that it is upper bounded by this mutual information, we are done. Okay, so remember that, so we'll first show that this is upper bounded by I of u tilde y2. Okay, so we'll show that this is upper bounded by summation I going from 1 through n of I of ui tilde y2, where recall that ui tilde is m2 l2 and y1 I minus 1. Right? So the goal is to show that this quantity is upper bounded by this quantity. Okay, so now I have m2 l2. I need y2 I minus 1. Correct, and for this, all I'm going to do is that this is less than or equal to summation I going from 1 through n. So we have one term m2 l2 y2 of I given y2 I minus 1. All right. Now, if you look at, I somehow want to get at least this particular term, m2 l2 y2 I minus 1. And I have one term over here. So there's one more term which is missing, which is simply I of uh, y2 I minus 1 y2 of I given m2 l2. All right. So certainly mutual information is always non-negative. So this term is less than or equal to the sum of these two terms, right? But just by using the chain rule on this term over here, this is equal to the mutual information between m2 y2 I minus 1 and y2 of I. Correct? So this point just used the chain rule. So this is because the second term is non-negative. Term is greater than or equal to 0, and this step just followed from chain rule. Okay, so we have this, which is fine. Now ultimately what I want is not m2 y2 I minus 1, but m2 y1 I minus 1. All right, I want to replace y2 y2 I minus 1 with y1 I minus 1, because that really gives you ui tilde. Right, so let me also introduce y1 I minus 1. Okay, and how can I do that? So once again, I use a similar trick. I introduce a new mutual information term, and then I use chain rule. So I going from 1 through n of the mutual information between m2 l2 y2 I minus 1 y2 of I plus the mutual information between y1 I minus 1 and y2 of I given m2 l2 y2 I minus 1. Okay, and this is, and I can write this because this second term is non-negative, right? So obviously this term is less than or equal to itself plus some non-negative term. Okay, so now that we have this, let's use the chain rule. Right, so if I use the chain rule, I get that the sum of these two terms is equal to the mutual information between m2 y1 I minus 1, y2 I minus 1, and y2 of I. Okay, so that is fine. Uh, but now, but now I have this extra term over here, y2 of I minus 1. Right, I somehow need to eliminate this particular term. Okay, and I and to do this, let's just try to write out what this mutual information is. Right, so the mutual information is h of y2 of I minus h of y2 of I given this particular quantity, which is m2 L2 y1 I minus 1 y2 I minus 1. Now, I claim that the second term, the entropy or the conditional entropy of y2 of I given m2 y1 I minus 1 and y2 I minus 1, this is equal to the conditional entropy of y2 of I given just m2 L2 and y1 I minus 1. So this is not required at all. Can can someone tell me why? So I have h of y2 of I, maybe let's just take y2 of 1 given m2 L2 y1 I minus 1, sorry, let's maybe take y2 of 2. So that would be y1 of 1, y2 of 1. Okay, and the claim is that this is equal to the entropy of y2 of 2 given m2 L2 y1 of 1. Any comments as to why this is true? Look at this particular Markov chain over here, right? So this chain like this, right? So this forms a Markov chain, right? So conditioned on y1 of 1, y2 of 1 and y2 of 2 are actually independent of each other. All right. So you have a bigger Markov chain. So this implies that y2 of 2, y1 of 1 and y2 of 1 forms a Markov chain. Or y2 of 2, m2, l2, y1 of 1, y2 of 1, these form a Markov chain. Correct? So really if you're given y1 of 1, y2 of 1 and y2 of 2 are conditionally independent. All right. So, and that is why I can write this conditional entropy as this particular conditional entropy. Now, in general, if you take any I, you always have the following Markov chain holding true. So, y2 of I, m2, l2, y1, I minus 1, y2, I minus 1. So, this always forms a Markov chain. And, and that you can see from here. So you look at y2 of I, okay, and you have this tree, right? You have this all the way up to n minus 1, y2 of n minus 1. So this is one set of variables that we are interested in, which is this quantity over here. Another set of variables that we're interested in are these and this one, correct? So the ones in gray, the random variables are the random variables marked in gray are really the random variables that we're interested in. And clearly, if in this tree over here, if you remove all of these, if you just break them out, then clearly this forms one independent component, whereas the rest of these form another independent component. So if you condition on these random variables, then these random variables and these random variables, these are independent. Correct? So in general, I have h of y2 of I given m2 l2, y1 I minus 1, y2 I minus 1. This is equal to the conditional entropy of y2 of I given m2 l2 and y1 I minus 1. Right? So if I give you the output of the first channel up to the I minus 1th time instant and the message of the second user, then what is received at the current time instant is conditionally independent of everything that was received by the second user in the previous I minus 1 time instance. Okay, so let's use that over here. If we use that over here, then we get that this is less than or equal to the mutual information between m2 l2, y1 I minus 1 and y2 of I. But this is simply ui tilde, right? So this is just ui tilde. So this quantity is the mutual information between ui tilde and y2 of I. Okay. I can just write this as n times some mutual information between u bar and y2. Okay, so that's great. Uh, so now I have n times r1. Sorry, this is yeah. So we've already shown that n times r1 is less than or equal to n times the mutual information between x and y1 given u bar, and similarly. Right now we've shown that n times r2 is less than or equal to, we have this being less than or equal to this mutual information over here, right? It's this mutual information over here plus some small term which depends on the entropy. And we've shown that this term is less than or equal to n times this mutual information. So this is less than or equal to n times I of u bar y2 plus whatever h of pe plus nr1 times pe. All right. So therefore, if we have a scheme for which the probability of error is vanishing in n, then R1 must be less than or equal to I of x y1 given u bar, and R2 must be less than or equal to I of u bar y2. Okay. So this is true. True. No matter which encoder and decoder you use. Right? Because in the entire proof, we didn't assume anything about the encoder and decoder, except that the probability of error is vanishing in it. So as long as you have some set of encoders and decoders, if you want the probability of error to be small, then R1 must be less than or equal to this, and R2 must be less than or equal to this. If not, then this quantity will be large, right? Because this quantity is lower bounded by nr2 minus n times this mutual information. So if R2 is larger than this quantity, then this means that this quantity will also be large. And that obviously implies that the probability of error will also be large, right? So if you want the probability of error to be zero, to be vanishing in n, then R1 must be less than or equal to this mutual information, and R2 must be less than or equal to this mutual information. All right. But of course, in deriving this, we assume that u bar is large, right? So the auxiliary random variable is large, but it turns out that you can prove separately that the size of the auxiliary random variable need not be too large. The support of the auxiliary random variable can in fact be very small, but that uses a different technique called the convex cover method, and I won't describe that in detail now. So if you're interested, then you can just go through Appendix C of the El Gamal and Kim textbook. What it basically says is that since this region is convex, all right, since this region is convex and it's described using this auxiliary random variable, you can always redefine the auxiliary random variable such that the auxiliary random variable has a very small alphabet. Okay, and in fact, the size of the auxiliary random variable can be as small as the minimum of the size of x, size of y1, size of y2 plus 1. It doesn't have to be any larger than that. Okay, so this completes the proof of the outer bound for degraded broadcast channels. Note that we used degradedness through this Markov chain. Right? We assume that these random variables form this particular Markov structure over here, and that was used a lot in the proof. Right? If this Markov structure does not hold, then the proof does not go through. Okay, so this set of bounds that we just derived is valid for degraded broadcast channels alone. All right. So the capacity region for any two user discrete memoryless degraded broadcast channel is given by this. So it is a set of all R1, R2 satisfying these two mutual information inequalities. All right. Any questions? All right. So let's see. So we've seen this mutual information term. Right. So we derived an outer bound, and this gives us the capacity region of any two-user degraded broadcast channel. Now, in many applications, what we're interested in is evaluating this capacity region. Right. After all, that is as a system designer, that is what we are really interested in. Given a particular channel, maybe it's a Gaussian broadcast channel or some broadcast channel with some constraint. Maybe the constraints depend on the modulation scheme that you use. So that defines, so you have some broadcast channel, hopefully it is degraded. And for this channel, you have to evaluate the capacity region. All right. And we saw that we can do this numerically. We saw some examples where we numerically evaluated the region which can be achieved using superposition coding. And we saw that that's better than what can be achieved using TDMA. But in general, if for example, if the input alphabet is large, then this capacity region can be hard to compute. All right. We saw that when we were doing the simulations, when we were trying to numerically evaluate this, even for binary input, binary output broadcast channels, it takes some time. It takes some time to evaluate the capacity region, and in fact, this at least the way we implemented it, evaluating the capacity region takes time, which is exponential in the size of the alphabet. So the complexity is exponential in the size of since the auxiliary random variable is the largest, the overall complexity is exponential in the size of the auxiliary random variable. All right. In fact, it's at least the way I implemented it, it's exponential in the size of the auxiliary random variable times the input alphabet. Right. So even for the binary, even for binary input channels, binary input, binary output channels, the complexity is exponential is roughly 2 to the some constant times 6. Right. So the size of u is the minimum of the size of x, size of y1, size of y2 plus 1. So size of u is 3, and the size of x was 2. So this grows as 2 to the some constant times 6. And if you increase the size of the input alphabet, so for example, if you had let's say quam, right? If you used 4 quam as your modulation scheme, and let's say that even at the receivers you quantized it to something, then this complexity is still this complexity immediately becomes 2 to the whatever 5 into 4. All right. So 4 quam, size of u has to be 4 plus 1 5. So this is 2 to the 20 already. All right, which is fairly large, and the bigger this becomes, even as soon as you take it to as soon as you double the size of the alphabet, even 8 quam, this becomes really large. Right. So in general, evaluating this capacity region is difficult for a general broadcast channel. But as we'll see a little later, for certain broadcast channels, this can be simplified. If you know how to identify the auxiliary random variable and get a closed form expression, then this becomes much easier, and you can exactly evaluate what the superposition coding region is. Okay, so we'll do that for 2 channels. One, we've already done it for the binary symmetric broadcast channel, and later on we'll do it for Gaussian broadcast channels. All right, but the point here is that for general, even degraded broadcast channels, with even reasonably small input and output alphabets, evaluating the capacity region is hard. All right. So let's look at the binary symmetric broadcast channel. Okay. Earlier, we did derive an achievable rate region, and that achievable rate region turned out to be the following. Right. So it is R1. So R1, R2 is achievable for the binary symmetric broadcast channel if R1 is less than or equal to h of alpha star P1 minus h of P1, and R2 is less than or equal to 1 minus h2 of alpha star P2 for some alpha between 0 and half. Okay, and that is what, and so this can be achieved using superposition codes. And we'll see that this is now, in fact, the best that we can possibly hope for. All right. So recall that the binary symmetric broadcast channel is the following. So the input is binary. The outputs are both binary. Y1 is obtained by passing X through a BSC P1, and Y2 is obtained by passing X through a BSC P2. All right, where we're always assuming that, since we're assuming that user 2 is degraded with respect to user 1, we're assuming that P2 is greater than P1. And let us also assume that P2 is less than half and P1 is greater than 0. Okay, so for this particular broadcast channel, we want to know what the exact capacity region is. All right, and so this binary symmetric broadcast channel, if you look at the physically degraded version of this, then you can think of it in the following sense. So you take X, you pass it through a BSC P1 to get Y1. This is what receiver 1 sees. And Y1 is passed through another broadcast channel, a BSC P2 tilde, to get Y2. All right, where this P2 tilde is chosen so that P2 is equal to P1 star P2 tilde. So this is just P1 into 1 minus P2 tilde plus P2 into 1 minus, sorry, P2 tilde into 1 minus P1. Okay, so the capacity, we've seen that, so this is the physically degraded equivalent of this particular channel. And both these channels, note that these two channels are different, because in this channel, this BSC and this BSC are statistically independent of each other, whereas in this channel, the channel to Y1 is not statistically independent of the channel from X to Y2. But both these have the same capacity regions. Both have the same capacity region. And that is because the capacity region only depends on Py1 given X and Py2 given X, and not specifically on Py1, Y2 given X. Okay, so we have this. Okay, and for this we want to know what is the capacity region. We know that for any general channel, any general degraded broadcast channel, this is the capacity region. R1 is less than or equal to I x y1 given U, and R2 is less than or equal to I U y2. So this is true, but identifying the correct U is not easy. All right. So it's possible that you get so you choose one particular U to get this rate region, and that is achievable using superposition codes. But to show that this is the best that you can achieve, you have to show that no matter how you choose U, R1 and R2 are always less than or equal to this. Okay, so this is the capacity region. But we're not sure what is the best PUX to choose, right? Uh, so let's see, how do we get this rate region from this rate region? Right, so we have this. This is, we know that this is the capacity region. So let us make one particular choice of PUX. Right, so how do we choose PUX to evaluate this? Correct. So let's start with one particular choice. So choose U to be Bernoulli half. Okay, let's choose U to be Bernoulli half, and let us choose X to be equal to U XOR some W, where W is Bernoulli alpha. Okay, so U is Bernoulli half, and Px given U of X given U, so it is equal to, so if W is equal to X, sorry, if X equal to U, then this is, okay, sorry, let me, so this is Bernoulli alpha. So this is 1 minus alpha if X is equal to U, and it's equal to alpha if X is not equal to U. Okay, so you first generate a U which is Bernoulli alpha, and then given a particular U, given a particular realization of U, you choose X by passing U through a BSC alpha. So that gives you the joint distribution. So you have U, which is Bernoulli half, and you pass this through a BSC alpha to get X. All right. So note that this is not actually the channel. This is how you just choose these distributions, or in other words, this is how you choose the code book. Correct. So you are going to generate UN 2 to the NR2 code words UN Bernoulli half. So you're going to choose 2 to the NR2 code words which are uniformly spaced in the binary space, and then for each UN, that is for each cloud center, you will generate the satellite code book such that all the satellite code words are within Hamming distance n times alpha of UN. All right, so this is right. So these are the UNs, and for each you will choose code words. The satellite code words which are within some particular region, right? So the distance between these two is at most n times alpha. Okay, so this is PU and PX given U. Correct. So now let's see what this evaluates to. So this gives us some mutual information bounds. So this gives us some R1 is less than or equal to something and R2 is less than or equal to something. Let's try to evaluate that. So for this particular choice of PUX, R1 is less than or equal to I of X Y1 given U, right? Which is H of Y1 given U plus, minus H of Y1 given X U, right? So let's think about what we have. So what does the entire distribution look like? So you have U, which is Bernoulli half. You pass U through a BSC alpha to get X. You pass X through BSC P1 to get Y1, and you pass Y1 through BSC P2 tilde to get Y2. Correct? So now, what is H of X given U equal to? We are passing U through a BSC alpha, all right, and to get X. So what is H of X given U?
One, okay, sorry. H2 of it will be this
Correct. H2 of?
H2 of half asterisk will be using half of one
No,
second, sir.
you don't need that, right? So that is U. You just need alpha, right? So this will just be
Alpha.
H2 of alpha,
Okay, sir.
correct?
Hmm.
So similarly, what about the equivalent channel from U to Y1? H of Y1.
Alpha P1.
Exactly. So it is H2 of alpha star P1. Right. So good. So we have one term already. So H2 of alpha star P1 minus, we need H of Y1 given X comma U. Right. So Y1 given X and U. But what is H of Y1 given X U equal to?
Can we say H2 of P1, sir?
Exactly. So it's equal to H2 of P1. Why is that the case?
Independent.
Correct. So this conditionally independent, right? So
Yes.
U X Y1 forms a Markov chain. So given X, Y1 is independent of U. So this is just H of Y1 given X, and H of Y1 given X is just the binary entropy of P1. Okay, that's good. Now let's look at R2. So we know that this is less than or equal to I of U Y2. All right, so which is H of Y2 minus H of Y2 given U. So what can you say about the equivalent channel from U to Y2? So it's going to be, since it's a concatenation of multiple BSCs.
Three different bases.
Yeah, so what kind of a BSC is it?
Can we say asterisk of all three, sir? Alpha asterisk P1.
Exactly. It's alpha star P1 star P2 tilde. But what is P1 star P2 tilde equal to?
In
It's
terms of expansion, sir?
Yeah, so it's just P2, right? So So
Okay.
P1 star P2, we chose P2 tilde such that uh, we chose P2 tilde so that P2 is equal to P1 star P2 tilde. Correct? And as long as P2 is greater than P1, we can always find such a P2 tilde. All right. So you pass this through the BSc to get Y2. Correct? And so we know exactly what h of Y2 given U is. It is minus H2 of alpha star P2. But what about h of Y2? What is h of Y2 equal to? So we know that U is Bernoulli half. If you pass a Bernoulli half random variable through any BSc, what can you say about the output random variable?
Will it be h2 of
Energy.
half?
Yeah, exactly. But what is h2 of half equal to?
A point 5. Just 1 second.
No, no, no.
0.3, sir.
No,
0.30.
no.
It will be capacity kind of maximum.
No, no. What is h2 of half equal to?
One.
Yeah, exactly. It's just 1, right? Right, so it's just 1 minus h2 of alpha star p2. Right, so R1, so if we choose PUX in this particular fashion, then we get that R1 is less than or equal to H2 of alpha star P1 minus H2 of P1, and R2 is less than or equal to 1 minus H2 of alpha star P2. Right, so it is possible to choose a PUX which gives you this particular rate region. But we don't know if this is the best that is achievable, right? So this gives an inner bound, and it basically gives us this inner bound over here. But can we do better than this? Right. So that's the question. Right. So is it possible to choose a PUX? Can we do better by choosing a different?
Sir, there is some noise
Yes.
disturbance. We are not
Uh,
able.
Not audible now.
Now it is, sir. Some glitch might be.
Okay. Okay. Fine. So as I was saying, it's all right. So can we do better by choosing a different PUX? Okay. Yeah. So if I choose a different PUX, maybe with a larger uh, auxiliary alphabet, then can I get a better rate region? Right. So this rate region is achievable for one particular choice of PUX. But maybe it's possible to choose a different U and a different PX given U, for which I'll get something better. But in fact, it turns out that that is not possible. All right, and the way we show that uh, is using the following tool, which we learned much earlier, and that's Mrs. Gerber's lemma. So recall that what Mrs. Gerber's lemma says, or the scalar version of Mrs. Gerber's lemma says, is that if you have any joint distribution Pxu, where x is binary and u can be any alphabet, it can be binary, ternary, quaternary, no, it doesn't matter. So if you pass x through a BSC P, right? So if Z is Bernoulli P and Y is obtained by passing X through a BSC P, all right, then H of Y given U is always lower bounded by this quantity. It is H2 inverse of H of X given U star P. So this is what we will use to show that no matter how you choose Pxu, the capacity region is always equal to this particular quantity. It is always equal to this. This is the best that you can hope for. Okay, and it's fairly simple, just a couple of lines. So let me try to complete it. So we start with the following things. So let's start with I of. So let's start with R2. Right, R2 we know is less than or equal to I of U Y2. Correct. So this is H of Y2 minus H of Y2 given U. Okay. So we know that Y2 is binary, right? It's a binary symmetric broadcast channel. So H of Y2 is always going to be less than or equal to 1. But we don't know what H of Y2 given U is going to be. Correct? So I'm going to define some beta such that this is, let's say that H of Y2 given U is equal to H2 of beta star P2. Okay. Since Y2 is a binary random variable and it's obtained by passing X through a BSC P2, we can always choose a beta such that H of Y2 given U is equal to this particular quantity. Okay. It's always possible to choose some beta which is between 0 and half, such that this holds. H of Y2 given U is equal to H2 of beta star P2. So you choose a beta such that this equality holds. Okay, so this means that for this particular choice of beta, R2 is less than or equal to 1 minus H2 of beta star P2. Okay, what we have to show to complete the proof, what we now have to show is that for this particular choice of beta, R1 is also less than or equal to H2 of beta star P1 minus H of P1, H2 of P1. Okay. But what do we know? We know that R1 should be less than or equal to I of X Y1 given U, which is H of Y1 given U minus H of Y1 given X and U. Correct? And so let's leave the second term, the first term as it is. We'll deal with that later. But we know that Y1 X U forms a Markov chain. Right? So conditioned on X, Y1 and U are independent of each other. This is equal to H of Y1 given X, but H of Y1 given X is H2 of P1. H2 of P1. All right. So we've got one term, right? And this holds irrespective of how you choose PXU. All right. So you choose any PXU, right? U can be any alphabet, doesn't matter. This always holds. All of these hold. Okay. So now all we need is a bound on H of y1 given U. Right? So we need a bound on H of y1 given U. What is the bound? Okay, so let's think about the relationship between y1 and y2. All right, so y2 is obtained by passing y1 through BSC P2. All right, and U is some joint. So U comma y1. So you have a U which gives you a y1. There's some, so y1 and U are jointly distributed according to something. Right? So if I apply Mrs. Gerber's lemma on this, then I get that H of y2 given U, let's go back to the definition of Mrs. Gerber's lemma. So H of y2 given U is lower bounded by this particular quantity. It is lower bounded by H2 of H2 inverse of H of y1 given U star P2 tilde, right? Because y2 is obtained by passing y1 through a BSC P2 tilde, right? And y2 is obtained by passing x through BSC P2. Okay, so but we already said that H of y1 given U, sorry, yeah. So but H of y2 given U is equal to H of beta star P2. H2 of beta star P2 is greater than or equal to H2 of H2 inverse of H of y1 given U star P2 tilde. Okay. Now all these terms, beta, P2 and everything else are between 0 and half. All right. And the binary entropy function, if you recall what it looks like between 0 and half, it's an increasing function. If you restrict the domain to through the interval 0 to half, H2 of P is increasing in 0 to half and it's invertible. All right, so beta star P2 is greater than or equal to H2 inverse of H of y1 given U star P2 tilde. Or beta star, so P2 is P1 star P2 tilde. So this is greater than or equal to H2 inverse of H of y1 given U star P2 tilde. Or this implies that beta star P1 is greater than or equal to H2 inverse of H of y1 given U, or H of y1 given U is less than or equal to, if I take H2 on both sides, this is less than or equal to H2 of beta star P1. All right, so I'm just plugging that back in here. So this quantity is less than or equal to H2 of beta star P1 minus H2 of P1. All right. So by varying beta, so no matter how you choose Pxu, R2 is always less than or equal to 1 minus H2 of beta star P2 for some beta between 0 and half. And R2, sorry, so this is R2, and R1 is less than or equal to H2 of beta star P1 minus H2 of P1 for the same beta between 0 and half. All right. So certainly the achievable rate region is equal to, so the achievable rate region can only be a subset of this region, and we know that every point in this region can be achieved just by choosing alpha is equal to beta. Right, so here alpha is between 0 and half, and we know that this is achievable using superposition codes, and we know that no matter how you choose Pxu, any rate point outside this region is not achievable. Okay, so therefore this gives the entire capacity region for the binary symmetric broadcast channel. All right. So let's stop at this point. Are there any questions?
No, sir.
Okay.
Sir, not with respect to this lecture, but otherwise, with respect to the presentation topic, like, okay, I mean, like, will it be okay if we can discuss at any other time than the class? If, because
I'm sorry,
some
Girish.
notations.
Your voice is very low. I can't really hear what you're saying.
Sir, I'm audible now, sir.
Yes, it's better now.
So what I was just asking, sir, will that be, I mean, will that be possible if any discussion sessions can be at any other time, not in the classes, regarding the presentation topics, sir? Like some notations are confusing, so if it is okay.
Sure. Yeah, we can have that. So it would be helpful if, I mean, I mean, one thing that you can always do is just whatever questions you have, you can always post it on Piazza. If there's a
Right, sir.
more discussion that is required, we can have a separate session for that itself.
Sure, sir. Sure, sir. Sure, sir.
All right. So maybe let us just initiate this discussion on Piazza, and then we
Right, sir.
can take it to a live session. So once we know exactly, or once we identify what exactly needs to be discussed.
Right, sir.
All right. Okay.
Right, sir. Thanks, sir.
Yep. Okay. So if there are no other questions, then let's stop at this point. So we'll meet tomorrow.